Hi everyone, welcome to the second video for Module 5 of KNES 7103, Design and Analysis 1, which is taught in the Department of Health, Kinesiology, and Recreation here at the University of Utah. Today we're going to be discussing how to interpret parameter estimates. In the previous video, the first video in Module 5, we talked about how we could actually calculate the slope and the intercept for a given set of values and find the slope and the intercept estimates that would provide us with the smallest sum of squared errors. In this video, we want to talk a little bit how to actually interpret those parameter estimates and how the values of those parameter estimates might change if the scale of x changes or if the 0 point on the x variable changes. So when we're talking about interpreting these linear parameters, we're using the data set that we used from the chapter and that we modeled in the previous video, in which we're looking at internet usage in various states as a function of college graduation rates within those states. So we're looking at percent household internet use and college graduation percentage in each of the 50 US states. And in the previous module, we talked about applying these formulas in order to calculate the slope and the intercept that would give us the smallest sum of squared errors, right? And we found a point estimate of 0.86 for the slope and 47.91 for the intercept. And if we were to actually plot this linear function, right, of the intercept plus the slope times the college graduation percentage, we would get a line that looks like this, the dashed red line here that's superimposed over the top of our data. So how do we actually interpret these numerical values? Well, the intercept is the estimated value of y when all x's are equal to 0. In this case, we only have one x, so the intercept of 47.91 is the estimated value when college graduation percentage is 0. And you can see if you follow the line that we've imposed over the top of our data, at 0% college graduation, we'd have an estimated 47.9% households with internet access. Now, one thing we want to be careful about is that this is actually pretty far away from our data. None of the states actually have a college graduation percentage of less than 20, but that is how we would interpret this intercept. Similarly, the slope is estimated is the estimated change in y for a 1 unit change in x. So if we start at this intercept, for every 1 point increase in college graduation percentage, we go up 0.86 points in terms of households with internet access. So for every 1 more percentage point of college graduation, we have 0.86 percentage points increase in household internet access. And as that slope is positive, right, you can see that as college graduation rates increase, household internet access increases at a slightly less than a 1-to-1 level, because both our y and our x are both in terms of percentages. And these general rules will always apply. So for any linear model that you have, right, the intercept is going to be the estimated value of y when all x's are 0, and the slope is going to be the estimated change in y for a 1 unit change in x. Right? And so that is always true. But the exact interpretation depends a little bit on what your x variable really is and what your y variable really is. So we're going to walk through a few different transformations to show you how this is going to change what we calculate in terms of the values here, but it's also going to change how we interpret those values. So first, as we said, in the untransformed case, right, this is our linear modeling formula in R, and these are the coefficients we get back. We would get an intercept of 47.91 and a slope of 0.86. So at a college graduation percentage equal to 0, we would estimate 47.91% households with internet access. And for every additional point we increase, we'd estimate a 0.86 increase in households with internet access. Now, if we transform this variable, right, it's going to actually change our interpretation. So we can center the x-axis on different values. In the previous untransformed example, 0 actually meant 0 households with internet access. However, we could recenter this on a different value and change the meaning of 0. So in this situation, we're actually going to create a new variable called college 50, which is the original college variable minus 50. And so what that means is we are centering this now on 50, or basically what centering means is we're changing what the 0 point means. So you can see here, we now on our x-axis have -100 to 0, where 0 is what used to be 50 in our data. So that we had less than 50% college graduation rates. Now 50 actually is 0 because this value was the original values minus 50. And you can see that this significantly changes the intercept, but it doesn't actually have an effect on the slope. Our previous intercept, right, was 47.91, and now it's 91.00, because 0 on the previous model was below, right, our lowest data points. That was the predicted value for states with a 0% college graduation rate. If we recenter this on 50, now the value of 0 is states that have a 50% college graduation rate. And states that had a 50% college graduation rate would have an estimated 91% of households with internet access. So all we've really done in this situation is sort of slid the data left or right, which referred to as a translation. We've translated the data to the left or to the right on the x-axis. That doesn't change the slope because it doesn't change what a 1 unit value of x is, right? This is a 1 unit change in x is still a 1 percentage point increase, so the slope has not changed. However, what 0 means has changed. And in our previous example, the intercept was somewhat meaningless because it was outside the lower range of our data. And in this example, it's also somewhat meaningless because it's outside of the higher range of our data, right? We didn't actually have any states with a 50% graduation rate. So we're extrapolating a little bit here, and that creates some uncertainty into the value of this estimate. We could, however, also pick a point in the middle of our data. So for instance, we could mean center our variable. So we're going to create a variable in R called college.c, where we take the original variable college, and from every score, we subtract the mean of that variable, right? So it would look something like this. We'd create x centered. And so for every x centered, it's equal to the original x minus the mean. So positive values were people who were above the mean, or I should say states who were above the mean, and negative values are states who were below the mean. And if we put this into our linear modeling formula in R, these are the intercepts we get out. 72.8, or 72.81 with rounding, right, and a slope of 0.8619. So again, our slope isn't actually changing because we haven't done anything to change the scale of x, right? A 1 unit change in x is still a 1 percentage point change. So the increase as we go along the x-axis is still the same. However, you can see that the intercept has now changed. It's no longer, 47 and it's no longer 91. It's actually somewhere in the middle, and it's 72.81. So that 72.81 is the value for the average college graduation rate because we've mean centered this variable. So now 0 on the x-axis translates into the average college graduation rate. And for states with the average college graduation rate, their estimated household percentage internet access, their estimated percentage of households with internet access is about 73%, right? So in this mean-centered case, the intercept actually takes on a much more reasonable interpretation, I would say, compared to the other two types of centering that we looked at. If we mean-center this, the intercept tells us, on average, what is the percentage of households with internet access. In the average state, we know that about 73% of households have internet access. But we also know that this is going to go up or down depending on what the college graduation rate in that state is. And for states with a below average college graduation rate, they'll be below this value. And for states with an above average college graduation rate, they will be above this value. So mean centering actually can make these very interpretable and actually improve what it means when we look at the intercept. Finally, we can also change the scale of x, right? So centering was just a translation in which we moved x left or right, but it didn't fundamentally change what a 1 unit increase in x was. If we were to change the scale of x, so let's say we divide x by 100, so rather than percentages, right, 80%, if I wanted to change that back into a proportion and make 80% 0.80, I could divide it by 100. Right, so we're going to call this college proportion or college.p, in which we take the original college variable and divide it by 100. So 90 becomes 0.90, 75 becomes 0.75, and so on. So we'll get a unique proportion for each state, which is based on their original x value divided by 100. And as you can see, the general relationship, the pattern hasn't really changed. But if we look at the percentage of households with internet access against the proportion of college graduates in each state, the scale of the x-axis is very different. So now we have 0 to 0.1 to 0.2 to 0.3 to 0.4. So changing that proportion is actually going to have a significant effect on our slope, but our intercept is actually back to what it was in the prior model, right? In the untransformed data, the intercept was 47.91, but the slope was actually quite a bit smaller. And you can see that when we contrast the two against each other. Again, you can see the patterns look very similar, right? They're both positive relationships. But when we have the untransformed data, our scale goes from 0 to 100. So a 1 unit change in the untransformed data, a 1 unit change in x is 1/100th of the total scale. When we've divided this by 100 to make it a proportion, a 1 unit change in x is the full scale. That's going from 0 to 1. Whereas here, going from 0 to 1 is a very small change. So in that situation, you can see, obviously, this one's easy because we just divided by 100. So our slope is actually just moving the decimal point 2 places, right? But here, it's an 86-point change, right? If we went from 0 college graduation rates to 100% college graduation rates. Here, it's a 0.86-point change if we went from 0 to 1. So changing that scale of x is going to have a significant effect on the slope, but it's not going to have an effect on the intercept, right? And similarly, translating x, right, centering it on different variables has a significant effect on the intercept, but it's not going to have a significant effect on the slope. And the point of walking through this is that as we encounter different types of x variables and we might want to translate them in different ways or scale them in different ways, right, we have to be very cognizant of what 0 means on the x-axis and what a 1-point change means on the x-axis, because that's going to have a significant influence on how we interpret the estimates that we get for both the slope and the intercept.